All right, looks like we got about half, so I assume more people will be coming in a minute or so. Good afternoon, everybody. Thank you for attending our SEI Philadelphia webinar. We have another great presentation this afternoon. It's the design and construction of the new Hawk Falls Bridge. I'm sure you've seen this around, so we're really excited to have this presentation for our group, our members here. So just for a little bit of housekeeping before we get started, just as you will be aware, the meeting is being recorded. Your microphone and camera has been disabled, and in this meeting there is the Q&A function. It's not the chat, it's the Q&A function. You can click on that and you can ask your questions there. Feel free to ask during the presentation. This way, if something's on your mind, you can do that, ask that question, and at the end, I will read the questions to Dr. Mott, and we can answer your questions there. And if you have any follow-ups, just go ahead and put those in. As for SEI Philadelphia, stay up to date with us. We do have our website there. If you ever want to get a hold of us, our email is listed, phillysei@gmail.com. And then as always, we do a lot of postings on LinkedIn. So to join us, there's a QR code. Get your phone out, click, take a picture, and that'll take you right to our ASE SEI Philadelphia chapter LinkedIn account and start following us, and then you'll get all the updates for all our presentations, socials, etc. Just want to give a shout out to our board members. My name is Mike Urban. I am the chair this year. Our vice chairs, Colin Drager, treasurer Greg Dunn, Alex Mancy is our secretary. Nathan Dubbs is our program director. He's been working hard getting these presentations for everybody. And Justin Banks, director of public relations. He's the one that's giving all the shout outs in LinkedIn and getting you these presentation advertisements over to you. And Kylie White is our deputy director, helping out Justin, and our past chair is Keith Merle. Just want to thank all our sponsors that contributed to our 2025 SEI Philly Golf Outing. We really appreciate your help and your support, especially goes to the scholarship for the local area students. And as always, save the date. We're looking to do this golf outing again. It's been a success every year we've done it. So we'll be sending stuff out shortly, but we're looking at, I believe, the first week of May 2026. We just need to confirm that with the course. Little change this time. We actually have some stuff filled in for upcoming events. Next week, next Thursday, we are doing our winter social at the Conshohocken Brewing Company. We moved it a little bit closer to the city, so hopefully we can see more Philly area locals get out there to our social. Then later in February, we have our yearly joint meeting with DVGI. This is going to be on the James Street Bridge. And it's going to be in person at Valley Forge Casino. And then in March, we'll be doing our student event at Villanova University. It will be a panel discussion, and then we will also open it up to young professionals as well, because we will be offering professional headshots that you can use if they need to update, their LinkedIn page or just have that going out in the world. And then March, we're looking to have a virtual technical session. We're working on that topic. And then on April 14th at the Inn in Swarthmore is the ASCE multi-tech dinner. And we're still, again, working on our presentation for the SEI breakout session. And as always, if you have any projects that you've worked on that you would like to present, please reach out to us and we can get you on the agenda. So I just talked about the winter social. Again, get your phone out, click on, take a picture of the QR code and you can register. This event is, it's $25. You get 2 drink tickets and small bites. It's always a good time. Come out, see everybody. It's a good setting to, talk shop and, not have to, worry about work. And then again, as I said, we will be doing a live in-person technical session with a joint meeting with DVGI. So again, come out, meet some your coworkers on the geotechnical side of the room here. We have a great presentation on the James Street Bridge. So again, there's a QR code if you Want to scan that and register. And talking about that student event, we were, granted a small grant for SEI Philadelphia. It's going towards our student event. So as I mentioned, we are looking to get headshots taken, some professional headshots. So that will be what we will be using for, this grant to help out the students. And as well as if your company has anything that they would like to donate, any kind of, swag or literature, please reach out to us and we'll make sure the students get that. And part of that SEI Futures Fund is, gifts from people like you and your companies. So again, here's another QR code, or you can go to asce.org, SEI Futures Fund, and you can donate anything that goes towards everything SEI. It's 100% towards SEI. There's no administration fees that go with that. Anything that you can help out helps SEI and helps out the students that benefit and young professionals that benefit from this. So that's all I have for the housekeeping here. So today I'd like to introduce our speaker, Dr. Frank Artmont. He's a PE. He's a senior engineer in the National Bridge Group of Majeski and Masters. And over the past 10 years, he participated in a variety of design, rehabilitation, research, and forensic investigation projects related to steel and concrete bridges. He's an active member of AASHTO and SBA. He's a PE in both PA and New Jersey, and he is a graduate of Lehigh University. So I will now turn the presentation over to Dr. Artmont, and we will get this started.
Thank you, Mike, for the introduction there. Let me get my presentation shared. All right, I think everybody should be able to see that now. So yeah, first I just want to say thank you to ASCE and SEI Philadelphia for allowing the opportunity to give this presentation. This presentation will cover the Hawk Falls Bridge, both design and construction. This title slide there, you can see a rendering of the bridge, and by the end you'll be able to see it almost fully completed. So the outline here, we're going to talk about an overview of the project, look at evaluation of the existing structure and the decision to replace it, design of the replacement structure, construction. We're not going to cover assessment questions. That's in there from a past presentation I used with these slides, but we'll do some question and answers at the end. And so I just want to mention before we move on that this project's kind of special to me in that if you look at this little snippet of a hand calculation or hand sketch I did, that date is 12/7/15, and that is the first day I started working at Majeski & Masters. So I have been working on this project since my first day at M&M. It's more than 10 years later. Still working on this project, but it's almost complete. RFI here and there, but this project is kind of near and dear to my heart for that reason. So the background, this is in Interstate 476 over Mud Run. It's in the middle of Hickory Run State Park in Northeast Pennsylvania. It's about halfway between Scranton and Allentown there, north of Philadelphia. If you just go up the Northeast Extension, you'll eventually get there. The bridge is named for the nearby waterfall on Hawk Run. That Hawk Run flows into Mud Run upstream of the bridge. The picture of the waterfall is there. If you go up here in the summertime, there's a lot of people actually swimming in that swimming hole there, jumping and sliding down the waterfall, even though there's big signs that say everywhere, do not swim here. People tend not to listen to that. So the existing bridge, it's a 738-foot long, 3-span deck truss bridge with I-beam approach spans. You can see some images there, both from down in the valley and then from up looking down the roadway. It was designed in the 1950s by Majeski & Masters, so this is another one of our designs. This is actually was stamped by Frank Masters, one of our namesakes. The roadway is about 200 feet above the elevation of the stream, and this existing bridge had 2 lanes in each direction and basically no shoulders, just very, very small shoulders. As you might think about with the 1950s truss, you can go out and look at the existing structure and you see section loss in all the typical places, just above members and gusset plates. You see pack rust between the components of the members, and then you see bearings that look not very good at all. They're very corroded, not functioning as intended. There's also an interesting fact about this bridge, which I happen to notice every time I'm up on site, the existing bridge. For those of you who work on old trusses, there's basically three types of members you might encounter, compression members. You get your laced members, your batten plated members, and then your members with perforated cover plates. And for some reason, this existing bridge has all three of those. It's kind of interesting to look up and see kind of the history of truss construction in one structure. So the existing structure is nearly 70 years old and has multiple structural deficiencies. Actually, it's probably more than 70 years old now. The minimal shoulders make the existing bridge functionally obsolete. And because it's a truss, it contains NSTMs, which require more frequent and more stringent inspections. Rating work was performed to examine as built and as inspected capacity of the structure, including all the truss members, the floor beams, the stringers, and all the connections. And then from that, the necessary repairs or retrofits to carry modern loadings could be established, as well as a cost estimate. And so one of the big things is that the pack rust and crevice corrosion cannot really be addressed via repairs unless you're talking really extensive work. And that kind of limits your service life. You can use the typical pack rust approaches like, heating it up and trying to hammer out the pack rust, but that really doesn't work for a very long period of time afterwards. So the expected additional service life would be, 20 years more. And then significant additional work would be required to ensure that the service life could be upwards of that 20 years. You can't really widen the roadway here to meet to have full shoulders to meet modern requirements. And as I mentioned, the structure has a lot of NSTMs that, it's difficult to handle those unless you do some sophisticated analysis. So the evaluation assumed a new deck and new stringers, and then it required structural repairs to get a rating factor above 1.0 with current live loads for 53% of the truss members, 76% of the gusset plates, and essentially all the floor beams. So the cost estimate for that was approximately $30 million back in 2012 for 20 years additional life. And then also back in 2012, the new structure, which would be designed for 100-year service life, the cost of that was approximately $60 million. So it's, you get a brand new bridge, you get 5 times the life, and it's only twice as much. So it's kind of a no-brainer there, why the PTC decided to replace the structure. So the replacement structure selection, with the evaluation performed, like I said, it's determined that a new structure was needed. 3 options were investigated during preliminary design: a steel girder option, a steel arch option, and a concrete segmental option. The estimated costs for each option were relatively similar, and the steel arch option was ultimately selected because of aesthetics, the site conditions, and that's specifically because there was competent rock near the ground surface in the gorge there, which made a really good foundation for the thrust of an arch. And then in addition, the arch could easily be designed to accommodate additional traffic lanes in the future if that ends up being desired at any point. So the general plan is shown here. Straight alignment, nothing too crazy. The new bridge is on an entirely new alignment to the east of the existing bridge to avoid the need for staged construction or demolition, keep traffic flowing on the interstate and the turnpike throughout the entirety of construction. And then the existing structure will be demolished once the new structure is built and open to traffic. Here's the general elevation and layout of the steel arch structure. The total length is 720 feet between abutments, and the bridge is broken up into 12 60-foot panels. And the arch supports the inner 8 panels. The arches are pinned at their connection to the skewbacks or the arch foundations. That's the concrete, the big concrete wedge supporting the arch. And so it's pinned there so that vertical loads aren't causing any moments at the end of the steel arch rib. So you can kind of just design those skew backs for a directed thrust force. The structure is essentially symmetric about midspan, except that the roadway slope is a constant 1.4% grade along the length going to the north or south, from the south to the north. And that results in the columns being a little shorter on one side of the middle of the arch. Each arch rib line is made up of 11 segments. You can see the field splice segments shown in this image here. If I do my laser pointer here, you can see the field splice segments shown here. The little splice plates are drawn. And you note that as you get to the center of the bridge, they get shorter and shorter. And this is done to ensure that the constructability of the structure was easy. As you need to extend a crane further out for those picks that are further out into the middle, the structure gets lighter. It makes it a little bit easier. The erection sequence that we considered was using a large crane behind the abutments. And like I mentioned, as the crane needs to reach out further, which from behind the abutment, that's a pretty far length. You got to make sure that the sections aren't too heavy. The cross-section view of the bridge is shown here. It's pretty unique for arch structures in that there's 3 arch lines. Usually it's 2, sometimes 4, sometimes 3, but 2 is pretty common for most arches. The overall load path is, the load goes from the deck into a girder floor beam system. The girders and floor beams are at the same elevation. And then into the spandrel columns that go down into the arch ribs. Off of the arch, the columns just go into foundations that are either founded on the skew back or founded on column footings further up the sides of the gorge. All of the girders are rolled W36 shapes, and they are moment connected and continuous across the floor beams. So there's pretty big tie plates that connect the girder flanges over those floor beams. The floor beams are built up welded I shapes. The length over the center arch is level, and then there's a break point, and then they slope downwards at 3% near the outside. This is to kind of match the deck profile, which is a little bit more complicated of a shape. It's got a slope to the inside at the inside shoulders, but in order to avoid having to fabricate all of that into the floor beams, it kind of just generally follows that shape. There's varandial struts that connect the arch rib lines to provide bracing rather than like a typical X bracing system. This reduces the number of connections and gives a more open feel to the arch as a whole. So obviously this is the kind of analysis or kind of design you do a 3D FEA for. So we use Lucis FEA model to develop the design forces. So including dead load, cambers, live load, wind load, thermal, you name it, we did it. Beam elements are used for mostly everything: arch ribs, the struts, the columns, the girders, the floor beams, lateral bracing. Deck is shell elements, and then the floor beams and girders are composite with the deck, and so they're modeled in the same plane with eccentricities assigned using like a plate on eccentric beam type of approach. So now we're going to kind of start with the foundations of the bridge and work our way up through the design. So the skew backs, which are the foundations of the arch, were cast in place reinforced concrete on the sandstone bedrock. While they're founded on bedrock, the bearing capacity of the sandstone was somewhat limited, and that's the reason for the extremely large bearing surface. So, in this image here, you can see that it's 26 feet, kind of in the front to back direction, and it's also about the same in the direction in and out of the page here. It's only a pretty small portion that ends up sticking up above the ground, as you can see in the picture on the right. The angled surface meant that no friction was required to resist thrust. The angled back surface where it impacts the rock. But horizontal steps were provided in the bearing surface so that the skew back didn't slide prior to that arch thrust being placed on it. The second column from each end of the bridge is also supported on the skew back directly. You can see that in up here in the column center line up there on the top. Most of the skew back is buried, like I said, only the stem protrudes out. Just above this, at the ends of the arch, we have the pin bearings. And so these bearings were designed pretty much so that they would never need replacement. And that that resulted in the use of a lot of interesting materials here. The pin plates, which are the plates that thicken up the arch rib webs near the base of the arch, these plates here, those are actually A709 grade 50 CR, so kind of a poor man's stainless steel. The reason for using that was because we were concerned that with moisture getting in between the bearing plates for this bearing assemblage that mounts on the skew back, it would be difficult to have that dry out, and so we were worried about weathering steel actually being perfectly functional in there. The base assemblage was hot dip galvanized, and then the pin itself, the pin caps, the rod that goes through the pins, those are all stainless steel. We did make a pretty sophisticated matrix here to make sure that there was not going to be any galvanic corrosion, you know, what was in touch with what could be bridged over with liquid, and make sure that we wouldn't have any, you know, anything trying to bleed off to protect some other component. One thing that's unique about this is there are actually two pins. Each web gets its own pin. Usually when you see these, there's a single pin all the way across. This just made the pins easier to handle. And you don't have pin where it's not actually doing anything kind of in the middle there. The arch rib box itself was about approximately 7 foot wide, or 7 foot deep by 4 foot wide. And that's enough for a maintenance or inspection worker to be able to climb through without stooping over too much. And that makes it a lot easier. You know, from talking to our inspection guys in the office here, you know, when they're crawling around or they got to bend over to get through one of these all day, it really takes a toll on them. So we were trying to make it so that you can pretty much stand up in this box without too much effort. The plates which make up the section range from 1 inch to 2 3/4 inch thick, depending on the location. All of it is grade 50 weathering steel. That's the brownish color of the structure that you saw in the pictures and renderings earlier. Diaphragms with access holes are present along the length of the structure, basically anywhere where a column comes in, and at certain points to just enhance the stiffness. The typical diaphragms are perpendicular to the arch rib, whereas the ones at the columns are actually aligned with the columns. They're near vertical. So that's kind of interesting. When you're walking through, you get to a diaphragm that's slanted with reference to the arch rib, and you know exactly where the column is, because when you're walking through these ribs, you can't really tell where you are. It's just, you know, you kind of know by the slope of the arch rib where you are and those diaphragms. The field splices mentioned earlier are made up of splice plates both inside and outside of the webs and flanges, and they also connect the stiffeners on each side of the splice. The splices were designed assuming all the load is transferred through the splice plates, with no load assumed to be transferred in bearing between the ends of the arch rib segments. And we do this, this is something M&M does every time they design an arch, and that's for constructability purposes. In the past, when arches have had to, you know, be milled to bear or finished to bear on those surfaces, it makes it really hard to you know, get that done in the field. And it also kind of disallows for any adjustment later on. If you need to slightly kink the arch at a field splice, you can't really do that if you have it milled to bear and you're taking a lot of force through just the bearing of one arch rib segment on another. So the arch analysis and design, you know, setting up an efficient arch shape requires development of the funicular polygon. So this is kind of the way they did it back in the day before computers and calculations, and we still do this to get kind of the most optimal arch shape. And so one way to think about this is, you know, an arch is somewhat just an inverted chain. And so if you look at the chain on the left there, you're applying loads, those big point masses, K, L, M, and N. They have different weights. And when you apply those, the cable goes to wherever it wants to go for equilibrium. And so, you know, if you think back to your structural analysis classes in college, at each, you know, node C, D, P, and Q there, you have to have equilibrium of forces. And so we do that basically the same way with the arch rib, although it's flipped over and all the forces are in compression instead of tension. And what this does is that if you set the shape right, you don't end up with moments under dead load. And so under dead load, your arch is just resisting compression. And then you have all that moment capacity able to take non-uniform live load. For the Hawk Falls Bridge in particular, the shape was approximated using a series of circular curves with different radii, and then there's a transition at each one of the column locations where there's a lot of load coming down. And so that minimizes the amount of moment that we have to carry through dead load. One of the other things we looked at is, buckling, because it's a compression member. We have to make sure that our buckling calculations are up to snuff. So we started with the AASHTO equations for determining the arch buckling load, and then verified that with refined analysis. And so one of the things you can do is an eigenvalue buckling analysis, and then your software will give you a P critical value, and you can plug that right into your AASHTO equations for the elastic buckling strength. And then we also did some nonlinear geometric analysis to verify that critical buckling load, and found about the same result. So the system of the arch ribs, we went with no X bracing to kind of improve the aesthetics, make the structure a little more efficient, and you can see that in the rendering how open the structure becomes below the deck. There's 8 strut pieces connecting the arch rib lines, 4 intermediate. Those are right here, and there's some on the other side. And then there's actually 4, 2 pairs of 2 right up here at the crown. They're all varendial braces, meaning that they're bracing primarily through their bending stiffness. And so at the connection between the strut and the arch rib, that's a moment connection to be able to get that moment stiffness. Now moving up to the columns and getting back up to the deck level there. So the columns are typically I-shaped with the flanges oriented parallel to the longitudinal axis of the bridge. So in other words, when the structure wants to expand and contract, it's placing the columns in minor axis bending. And so the minor axis bending is done on purpose to allow the structure to expand and contract and have some flexibility there. But however, that minor axis bending stiffness influences the axial capacity of the section. If you have too much movement, then you end up having a buckling problem. And so the tallest column, the one over the skew back, the blue circled here, that's actually a box shape for that reason. It's still pretty flexible because it's so tall, but we needed a little more strength in that direction to not have a buckling problem. For the shortest column, you tend to have the opposite issue where you don't have enough length and flexibility to actually accommodate the motion of the structure. And so at the green circle, there's actually a sliding bearing at the top of that column to avoid any kind of issues there. And then finally at the crown, the red circle, there's actually a fixed bearing at that point. And so all of the expansion and contraction of the structure takes place from that fixed point at the center of the arch, the crown, all the way to the abutment. So here's some details of the columns. The typical I-shaped columns are on the left there. You see there's a pretty typical connection. There's actually a stub welded onto the bottom of the floor beam, and then you can make a typical I-section type splice. The column lengths vary depending on the location you were at. And then at the base connection to the arch rib, there were plates that went down and attached the sides of the arch rib. And the web was attached with some welded angles there because they're not, an actual 90-degree angle. They got to be angled the same as the arch rib. On the right is the shorter column with the bearing on top. So you can see how short this column is, and you could imagine how much load that would attract based on the movement of the superstructure above the expansion and contraction. And so that's why there's a bearing assembly here. The box column details looks very similar. However, the base connection, this is where we're on top of the skew back. And so it's just a typical, base plate connection with some grout below, some leveling nuts, some anchor rods, that sort of thing. Up at the top, there's actually an I shape that's bolted onto the bottom of the floor beam, and then that slides into the box. This is the best way we could think of to be able to make this connection and still have it be adjustable depending on the position of the superstructure after construction. At the crown, so at the exterior and interior arches, there were bearings. At the exterior arch, there was no need for any kind of bolster or anything. The superstructure is almost sitting just right on top of the crown, or the crown of the arch. At the interior arch, which I don't have shown, there's a bolster that raises the bearing up to the bottom of the floor beam. So the longitudinal fixity is not taken by the bearings. It was a lot of force that was needed, braking and also the kind of the restraint of expansion and also live load. And so all of that needed a pretty large restraint system to keep the deck longitudinally fixed to the arch. And so we creatively called this system the longitudinal restraint. It's shown in this section here. It's basically a large, thick plate that is bolted on each side of the center arch, and it goes up, and there's some beams between some of the girders and the floor system, and there's some bearings there that allow some sliding back and forth if needed, and everything's kind of fixed longitudinally right there. So the framing of the floor system, the girders are spaced at 9 foot 4 3/4, and as I mentioned before, they're W36 beams. The floor beams are spaced at 60 feet and were welded I shapes, and the girders were continuous across the floor beams. To avoid an NSTM designation for those floor beams, since they are spaced at pretty far lengths, we did do a system redundant member analysis. So that is a pretty sophisticated nonlinear analysis where you essentially fracture the floor beam and ensure that the load can be carried elsewhere by other members. And we were able to do that. And so these floor beams don't need the typical NSTM type inspections. There's also a lateral bracing system provided here, which is designed to transfer all the wind loads. However, once the deck is on the bridge, that's going to take most of the wind load. But we did design that just in case the bridge ever needed to be redecked or anything like that. That's always there to take the loads. So one of my favorite things to say when we're talking about a big bridge design is wind tongue. And so at the ends of the bridge, rather than depend on bearings to take all of the lateral load from the floor system, the deck, the barrier, whatnot, all that wind load, and even some wind load from the arch that gets transferred up the columns, we designed this wind restraint system, or what we call a wind tongue. So there's a receiver that's mounted in the abutment, and then there's some tongue plates that are mounted on the end of the diaphragm. These are pretty big welded assemblages. And they allow sliding in the longitudinal direction, but transversely, it becomes the fixed point for all of the transverse loads on the superstructure. So I mentioned up front that this bridge could be easily widened. And so for this, the PTC usually typically plans for widening to the inside, which would have required 2 bridges here. But the better solution for this case was to widen to the outside. And so originally, when we started the design, it had 2 arches, and then during widening, another 2 arches would need to be placed on the outside. However, because of the need to not have to go through a lot of the permitting processes with the bridge being in a national or a state park, we decided that it would be easier up front to just design the 3 arches, the foundations, and everything for the widened condition. And so that's why a permanent arch rib got added. And whenever the PTC is ready to widen this area, that would just be done by bolting an extension onto the end of the floor beam, and that's where your additional, essentially, shoulder comes from. And then what used to be the shoulder becomes the 3rd travel lane in each direction. So now I'm just going to pop through some of the renderings that we had, before construction started, just from different angles, just so you can get a better idea in a 3D way of what the structure looks like. And then after we do this, I'll hop into construction and do about 15 minutes on that. All right, so getting into construction now. This is the original construction schedule. We of course blew through this in no time at all, and now the bridge is still being constructed. We ended up about a year behind schedule due to various reasons, but this is to be expected in a big project like this. The construction cost was $87.8 million. That's that's a little more than the 60 million we originally estimated, but part of that is due to the timing. This wasn't made until 2021. And part of that is due to the adding the third arch rib line for the additional widening, moving some of that work ahead till now. Steel fabrication started in late 2021 and continued through Q3 of 2023. Then substructure construction started in the second half of 2022 and was substantially complete by August 1st, 2023. And then the first arch rib segment was September 7th, 2023, and the final intermediate struts of the crown of the arch system were set on June 10th, 2024. The bridge deck was poured in spring of 2025, and then traffic started using the bridge, I believe, in August of last year. And then completion of construction is expected to be basically by the end of this year. And that includes demolition of the existing bridge and all the cleanup that goes along with that. So the construction methods here, they're a little different than what we anticipated during our design. So the design is on the left there, and what we anticipated was trying to stay out of the gorge as much as possible. And so we had some temporary stay towers mounted on top of that that second column, the one over the skew back, and then some stays that would be able to adjust the height of the arch rib and kind of cantilever out from there. However, the contractor, which was Trumbull, who won the project, they had some large temporary false work towers left over from previous work. And they felt more comfortable with using those and adjusting the geometry using those. And so they went ahead and got all the permitting done that they needed for their permanent or their temporary foundations and all that stuff. And then they ended up just supporting it from below, as shown in the image there. So that plan obviously required a lot more work in the gorge than was originally anticipated. They had to cut access roads down the sides of the gorge. And that got a little, that was another reason a little bit why the construction ended up a little bit behind schedule. And so the construction methods, both our original and Trumbull's, modified construction scheme required the use of a really large crane behind the abutment. And so the contractor used 2 of these Liebherr LR 11,000 cranes. And, you try to get an idea of the scale from these pictures, but until you're standing next to one of these things, you don't really realize how large they are. Each of these cranes took upwards of 50 truck deliveries to just get the pieces on site to be able to assemble them. It's hard to get a sense of scale from on the ground, but you can see during a site visit, that picture in the middle there is showing us walking along the crane boom as it was lowered to the ground. They actually had a pretty strict wind limit that they didn't want to go over. That was around 28 to 30 miles per hour wind. And so anytime that the wind was going to get above that, they would have to bring the booms down. And that, I don't recall exactly how long that took, but it wasn't like a 10-minute move. It was like more than an hour to get the boom out of the air and down on the ground. So it's hard to get a sense of on the ground, but when you start looking at these things from the air, you get a much better sense of how large these cranes actually are. And so they had enough reach with no load on them to be able to have the tips of the 2 cranes touch over the middle of the crown of the arch if they needed to. So just getting into the construction, the foundation construction first. The column foundations are shown here. This is the columns that were up the hill, not founded on the skew backs. They're just spread footings. You can see them. Both the foundations dug and then poured with the column there. There's a me for scale. So I think these are 10 foot by 10 foot wide columns. The height varied depending on the elevation of the rock, and so the tops of them were all the same. The skew back construction, largely the same for the columns. They got down to rock. They actually had we actually had in the plans to pour a 6-inch concrete, Class C concrete mud mat to protect the bearing surface. When they got down there, they were having trouble getting the rock to come out in the shape that we had, basically because it was sloped differently than the slope the skew back was needed. They actually eventually did use shotcrete for some of these rather than trying to form and pour the Class C. But that all worked out in the end. So here's a, on the left there is shown one of the skew backs before they buried it. You can see very, very large mass concrete pour. So on the right, this is actually, they had an issue with one of the concrete plants during one of the pours, and they didn't get enough concrete to finish the whole stem. We had to do some calculations to show that that would be okay. But because of that, we had the chance to actually crawl down in the cage when we were there for a site visit. And so this is inside one of the rebar cages. I mentioned mass concrete. You can see the black hoses there, which would be used for coolant during the mass concrete pours. The abutments are pretty typical Pennsylvania abutments. They did use the PennDOT drain trough detail. And although we did use strip seals for this bridge, we took a belt and suspenders type approach to say, well, they're strip seals. They're going to get pulled out by a plow or otherwise dislodged in the first 5 years. And then what happens to the water? And so the strip seals were actually placed behind the abutment right over this drain trough. And so if any leakage were to happen, it's going to go into the drain trough and drain away from the steel. Walls were needed to support that trough, and you can kind of see those in the left picture, at least the reinforcement there. And then on the right is kind of when they started backfilling, but the back wall of the trough hadn't yet been poured. Steel fabrication, this was High Steel in Lancaster did this work. On the left, it shows a picture of an arch rib with just the webs on only. You can see all the diaphragms. You could actually see where one of the column diaphragms is because it's sloped. It's this one right here, I believe. You can see all the cutouts for the stiffeners that had to go in. On the right, you can see the end of one of the arch ribs with the holes drilled for the pins, obviously before the pin plates get put on. We did have them actually line bore all of the holes for the pins. Oh, I don't know if you guys can hear that, but if it's too loud, I apologize. This is it's a line boring operation, so they're spinning down and making sure those holes are a precise diameter. They did this all at one time to make sure that all of the holes were aligned properly. High Steel did do a full laydown assembly in the yard, so this is a drone picture courtesy of them. You can see that they laid down the arch ribs and assembled them all together just to make sure that everything would fit in the field once they got up there. They also did a full floor system assembly too, and that's in that picture as well. All of the splice holes for the arch rib were subsized during fabrication and were reamed during this laydown to just ensure that everything fit correctly. Steel erection, so the end of the arch rib, or each of the arch rib segments was lifted into place by a crane, and then it was held on the crane until a sufficient number of bolts was installed to allow the crane to release. The process was repeated until the strut location was reached, and then the struts were installed and bolted up between arch lines. And then once all of the arch rib pieces were in place, each half of the arch rib system was lowered, rotating about the base pins until they mated near the crown. And then finally, the struts at the crown were installed and bolted up. And so the way they did that is, once they built enough arch rib segments out to the first tower, they would keep going to the second set of false work towers. And then at the second set of false work towers, the first set of false work towers would be disengaged at that point. And so they had pretty reasonable control to be able to lift the arch ribs up and down and make sure that the center crown lined up. Genesis Structures did the erection engineering for this. They had a lot of temporary works to be able to push the arch ribs around as needed to get everything to line up. When you're building from one side of a 480-foot gorge to the other, you got to make sure you're pointed in the right direction to end up at the right spot at the crown without having to put too much locked-in stress into the arch ribs. So here's a video I took. We had the opportunity to go out before they started putting the floor system and columns on. This was just after they had closed the arch ribs, and I'll just play this video pretty briefly. But this is me with a GoPro on my chest walking around the arch ribs up at the top of the crown. So you see the existing bridge there, a lot of the pack rust and whatnot you can see. They designed these pretty cool temporary platforms. You could see them there, that they actually just rotated with gravity. They were able to adjust them with come-alongs to be able to get down next to the arch rib and bolt all those bolts up, and also underneath as well. Here's another video kind of walking down. You can see the first set of columns there off of the abutment. They actually erected the floor beam and some of the column frames all at once while they had the large cranes on site. That made it pretty easy to make sure that everything was lined up correctly. They did that. They also erected full sections of floor system in the same way, as long as they had the large cranes on site to do that. And now I'll play a time lapse. So this is looking north. This isn't the full construction, but it gets through most of the superstructure. You can see here they're digging the foundations and pouring the skew backs. This is basically one day or one shot every day at around noon. So it's rather fast, but you get a scale of the advance of the construction as time goes on. See, if you look down in the gorge, you can see them digging one of those foundations out of rock for the temporary towers. Here's some temporary towers going up. The first set. They started setting arch ribs at this point. Now there is a stop here. We did have some concern when they set one of the first arch ribs that it was twisted a little bit. We weren't quite sure if that was a fabrication issue or something else. There was a lot of discussions between the contractor and the erection engineer and us over what should be done. Eventually, you know, the contractor kind of decided to go forward with it, and everything made it up in the end. So, it seems like High Steel's laydown did its job. If you caught it there, which I wanted to point out, but I kind of missed it. There's a point there where you can actually see the arches lower down, and that's when they're closing the arch rib. I think you can see it in the next time lapse looking south, and I'll try to point that out when it happens. You know, I do apologize. You know, I was just thinking maybe the time lapse might not be playing very well on your end. I'm not sure. Hopefully it is, but if not, I apologize for that. You see here they're putting the intermediate struts in, and all the other arch ribs are going in. Once they get up to the crown, if you watch closely, you'll see the arch lower right there. And that is when they lowered all the jacks, the hydraulic jacks at the falsework towers, and lowered the crown into position there. Here you can see them erecting floor system pieces, and they eventually did get rid of the large cranes and disassemble them, and then did the rest with either rubber. I believe they were all rubber tire cranes on crane matting out on the superstructure to erect the other stuff. And so here's the current state of what's going on out there. Image from below the bridge. Somebody, I think in our office or one of the other project partners, called this a cathedral of steel. And I fully agree with that. You look up and it's just tons of weathering steel with the stay-in-place forms. It just looks really clean and really nice. And then on the right there is the bridge open to traffic. It's currently carrying northbound traffic only. Due to there's an actual a second single span steel girder plate bridge north of the site here that had to be done with stage construction due to the traffic control and alignment. And so while that one's getting finished up, the alignment is such that only northbound is on the new structure. Southbound should be on the new structure sometime very soon. And then finally, I'll wrap up with the project team. So obviously the owners, the Pennsylvania Turnpike Commission. On the design side, you know, M&M is the EOR on this. Benish did our roadway. American Geotechnical and Environmental Services did the geotechnical. AD Marble Lotus did the environmental work. Corvin, which is now part of H&H, did the concrete concepts for the preliminary design, basically the segmental option. And then moving over into the construction side, the CEI was STV, and then Trumbull was the contractor, the general contractor. High did the steel fabrication, and then Genesis Structures was the erection engineering. So with that, I'd be happy to take any questions anybody has. Thank you very much.
Great. If you want to keep your presentation on,
Sure.
In case you just needed to go back, I just didn't turn anything off.
Make sure.
All right. We got some questions here, so I will just read them out. And I'll bring your presentation back on. There we go. So the first question here was, how much erection evaluation did you have to do prior to selection?
We didn't. I mean, this was one of those cases where we just have to show one feasible solution, right? This was a design bid build, and so just in our plans, we had to show one way of doing it. We did do some, if I'm remembering correctly, we did do some checks of, hey, when you have when you have like the first set of arch ribs out there, you don't have as much thrust as you would in the final condition, and so are the foundations still good for that? Because that pin is kind of out over the front of the skew back, you worry about the whole thing tipping over and rolling down the hill. We did at one point have rock anchors detailed at the back edge of the skew back to be able to take any of that kind of force depending on the construction. We eventually convinced ourselves it wasn't required. And so we did do some of those kind of preliminary engineering type studies just to make sure that what we were suggesting in our plans was feasible.
Great. Next question here was, if you had known the contractor means and methods as far as using access roads into the gorge for temporary support early on in the project, would that have impacted structure type recommendations to the PTC?
So I'm gonna caveat my response here with, I basically came onto this project right as final design was beginning. So I'm not aware of a lot of the preliminary design type discussions that went on. However, if I had to guess, I would say yes. I think if the PTC knew that they were going to go down in the gorge anyway, then a girder option or a segmental would have been maybe a lot more feasible, just because of being able to get down in the gorge and make kind of tall columns. However, from what I've heard about the preliminary and what I presented here, the cost estimates for all three of the options were rather similar, and I imagine in their cost estimate that we would have taken into account the need to cut access roads and all the concrete for taller columns and that sort of thing. So yeah, I don't know that it would. I certainly think it would have been a factor if they knew.
Great. Next question, as I understand it, the bearings at the crown don't have lateral restraint. What is the maximum lateral displacement at the crown?
I don't know. I think you're correct. If I'm remembering the details correctly, there is not much of a lateral restraint at the crown. I believe we had something temporary in there for just steel when it was just steel. But I don't believe the displacement was all that much, and especially in the final condition when you have the deck on, things not going to move around much at all. And so it becomes almost like a big simply supported beam between the abutments for that kind of wind load for lateral restraint.
Okay. Can you touch on the procedure for modeling the boundary conditions for each end of the spandrel columns? Did you just adjust the stiffness, or did you perform any localized models?
I believe we did. We did adjust some stiffness here and there. Like, we didn't just assume fixed or pinned. We did some adjustable stiffness type investigations there. I don't know if we did any local modeling. We may have. My personal involvement was basically anything concrete you see on this job, I was the designer for. And then one of the other senior engineers in our office did all the steel design, or most of the steel design. So I'd have to check in with her on local analysis models. But I do I do know that we had considered, hey, if it's not quite fixed to the arch rib, then you might have a different effective length factor for buckling. You might be transferring different amount of moment in. So all of those things, we definitely did consider those.
Great. How did you go about modeling the funicular form of the arch? Was this done using a physical model or other means? Also, were aesthetics a factor in selection of the arch shape, or was it purely structural? And thank you for your presentation.
Yeah, no problem. So the funicular form, that wasn't done physical. It was just done using like a spreadsheet equations. And so the way you do that is kind of the same way you do like a truss analysis. You kind of, it's almost like a guess and check approach, right? You figure out the nodal loads coming down from the columns, and then from there the angle that you need coming out of those two members in order to get no moment and be in equilibrium. And you kind of chase that all the way down to the foundation. Sorry, I forgot a step at the beginning there. The first thing you do is cable theorem, but it's reverse because it's in compression. You figure out your overall load on the structure, and you figure out the thrust at the base, depending on your rise to span ratio. And so that kind of leads into another question there. The aesthetics, the shallow arch was done for aesthetics reasons, but also because it kind of kept the big foundations out of the bottom of the gorge. Now, because of the way they did the construction, maybe that isn't as big of a factor. Although it still does keep inspectors from having to walk all the way down in the gorge to inspect, foundations or anything like that. They can all be reached from up on the hill and not have to go all the way down there.
Gotcha. Thank you. One more question here. Is the presentation PDF available? I can say that, this meeting is recorded. It will be on our SEI website and our YouTube page, but I'll leave that up to you if this is the presentation if you would like to share it.
I will check with, I'll check with the project manager on this project. I don't see an issue with sharing it, but I'd like to check just before I say, yes, it's going to be available.
Okay. So I guess, Bharat, if you reach out, we can put you in touch.
Yep. That sounds good. Yep.
Does anybody have any more questions? We have maybe one more minute. If not, I added the two links to our winter social and DVGI SEI joint dinner meeting in here. Actually, yes, we do have one more question. What is the advantage of providing 2 pins at each arch rib?
So, I mean, one of the things is you don't have to, the pin doesn't have to reach all the way across. It saves a lot of steel because the stuff in, the pin steel in the middle kind of isn't doing much. It allows a little more ease of putting the pins in. I mean, the pins are still heavy, but it's not, 3 times as heavy as one single pin would be. There has been other designs done with hinged arches like this, where essentially you have a big base plate at the bottom of the arch rib that has, a bunch of plates welded to it with holes in it. And so you end up with like a big, kind of interlocked finger type thing at the pin. And so in that case, you might have a large pin that goes across. But because we decided to connect the pins through just the webs, it made more sense to kind of have 2 pins down there rather than just one big one.
Great. All right. Well, with that, I'm going to wrap up. I'll share my screen now here. So on behalf of SEI, we thank you for taking your time and presenting to us. It was a great presentation. I will reach out, and as part of our appreciation, we'll be sending you this very fancy SEI Philly Yeti mug here for you.
Oh, thank you very much. I really appreciate that.
And then as for the posts, or I'm sorry, the PDHs, there's a link in the QA, as well as if you want to scan the QR code here, I'll leave this up for a little bit, and you can scan that and you'll get your PDH. So with that, thank you again very much. And this concludes our seminar for this month. And as I mentioned, go to the links down there, sign up for our DVGI SEI joint dinner meeting next month, as well as our winter social. Hopefully we'll get to see everybody out there and we can talk more. Thank you again, everybody.